Day 100 notes, pre-calculus. We made it to day 100 finally. Today we're going to continue looking at the graphs of logarithms and some of the properties of the graphs of logarithms. And to start off, I'd like for us to use our graphing calculator to graph the family of logarithms. And for the family, I want us to use the rule f of x is equal to logarithm base a of x. And what we're going to do is graph a function for each of these a values, 2, 3, 5, and 10. And while you're graphing these, I want you to think about what are the points that they have in common, what are some similarities between all of these functions, and what are some of the differences between the functions as well. So let's pull up our graphing calculator. We'll put a graphs page together. And what I'd like to do is create the function logarithm base, let's start with base 2 of x and graph that, and then introduce a new one, logarithm base 3 of x, and so on. I'm going to pause the video and put the rest of these graphs up on the page. And here we go with all four of those in place. The logarithm base 2 is the blue function, logarithm base 3 is the red, logarithm base 5 is the black, and logarithm base 10 is this pink graph here. And the question we have to ask ourselves is, does this make sense that the family of graphs looks this way? Does it make sense to you that this is how those functions should look? And hopefully you start to say, yes, this should make sense to you, or hopefully you understand why some of these features are true, or why they happen to be the case here. First off, let's notice that they all have the same point in common. They all have this point right here at 1, 0. So much like exponential functions always have the common point 0, 1, this one has the common point 1, 0. That's the inverse of 0, 1. And as far as the behavior for the others, hopefully you recognize that this is pretty accurate as well too. Let's consider this blue function up here. When x is equal to 10, which is this number out here, it takes a larger function value in order to satisfy this equation. 2 to some power has to equal x. Well, again, if we said that x was 10, 2 to what power would make this equal to 10. So we need a larger number to raise 2 to the power 2 in order to equal 10. Whereas if I'm looking at this pink graph, I need a smaller power to satisfy this statement. 2 to what power would equal 10? Again, we're looking at this when x is equal to 10. Well, 10 to the first power would equal 10. So that's why this is so much lower. The larger the base value, the shallower this curve appears to be, whereas the smaller our base value is, the steeper this curve tends to be. While we're talking about the family of functions here, I hope you recognize that limitation for what x or what our base is allowed to be. We talked about this at the very introduction of these logarithms, and you may or may not remember that a function, if it's going to have a logarithm, may not have a base value of 1. And do you understand why that's the case now? If I look at 1 raised to some function value, and that has to equal our target x, well, what if I had a target x value of 3? 1 to what power would equal the number 3? Well, hopefully you recognize that can't be done. 1 to any power will always be equal to 1. Since it's just a number that's multiplying by itself, we're not going to find a value to which we can raise 1 to get a value of 3. So remember, with our logarithms, a cannot be equal to 1. That's one of our major rules for logarithms. While we're on the subject of graphing logarithmic functions, let's talk about how we can manipulate a standard logarithmic graph into a position where we need it to be. Or in other words, we can consider how a basic logarithm can be changed by introducing outside values to the equation. So what should happen to the graph if I'm starting with logarithm base 5 of x? Logarithm base 5 of x would have been a graph that looks something like this. Okay, it's our regular logarithmic shape, and it's pretty shallow because the base is 5. What would make that change, or how would that change look when I introduce a value of 2? Now think way back to our shifts and transformations of functions. What happens if I take the number on the outside of the expression, a number on the outside of the expression, and I add to it? Does it stretch? Does it skew? Does it flip? Does it slide? What does it do to a function? Well, hopefully you remember that when we add a number on the outside of our function, adding a number to the outside is a vertical shift. So vertical shift. And since we are moving with a positive 2 value, this means that this is going to shift our function vertically up 2 units. So vertical shift upward 2 units. Whereas our original logarithmic function might have the intercept here at 1, 0, this new one would not have a point at 1, 0. Instead, it would have a point here at 1, 2. This is where it's been shifted upwards. And the graph of this function would come down and increase up and towards the right this way here. We can verify that with a graphing calculator, and here's a picture of that. Again, here's our 2 plus logarithm base 5. And if I compare that to our original logarithm base 5 of x, this one should be lower than the blue graph, and there it is right there. Our blue graph is above, it's been shifted directly upwards, whereas our red graph, which represents our original, is down below. Let's consider some other examples. h of x is equal to the logarithm base 10 of x minus 3. Well, here in this case, we've got a subtraction of a number, so that's a shift. We're subtracting a number. It's just like adding a number. That's shifting an object. Now, since this number is being subtracted from the inside of a set of parentheses with our function, that means it's a horizontal shift, so horizontal shift. And when we subtract 3, since we're applying a number on the inside of the parentheses, we need to be thinking of our opposite direction. This should produce a horizontal shift to the right 3 units. So if I were sketching this graph, it's going to be a logarithm that's relatively shallow. Here's my 1, 0, my standard starting point, but I don't have a point there. Instead, I must be shifted to the right 3 units, and I'm going to look for a relatively shallow logarithmic graph here. Additionally, remember, in none of our graphs before did we ever cross this y-axis. Well, that too got shifted to the right. So 1, 2, 3 units to the right. We should never have any values that cross this equation of x equals 3. Let's go take a look at this on our graphing calculator. Here's the graph of the logarithm base 10 of x minus 3. Notice the graph will stop here. It's not going to go any further to the left than x equals 3. And if I were to compare that to the original logarithm, whoops, let me try this again, tab, we'll call the logarithm base 10 of x without any changes. This is the one that's closer to the y-axis. You'll notice that it is just further to the left. The blue graph has been shifted directly to the right. What happens to a logarithmic function if we have a negative sign in front of it? This would be just the same as multiplying by -1. Well, since we're dealing with multiplication now, we're talking about a stretch or a shrink. Does this actually stretch at all, though? If its coefficient is 1, then there is no factor of stretching. So we're going to stretch by factor of 1, but again, stretching by a factor of 1 doesn't really change anything. But the big change here is because of that negative sign. The negative sign must flip this graph vertically because that -1 is on the outside. So if we flip it vertically, we're used to looking at a graph that might look something like this. Instead, I need to flip it vertically from top to bottom. And what we might end up with is something that looks like this. So let's go to the graphing calculator and check that one out. And here's a graph of that function, negative log base 2 of x. Let's see how that compares to the original. Here we have logarithm, whoops, let's try that again. Logarithm base 2 of x unmodified would look like this graph here. So again, this is our traditional graph in this red color. The blue graph then represents what happens when we multiply by a -1. What's going to happen if we multiply by a -1 on the inside of our function? Well, again, since we're multiplying, we're discussing about a stretch by a factor of 1. Well, again, since we're stretching by a factor of 1, that really doesn't change the size of this graph. But since it's multiplying by a negative number on the inside, this becomes a flip, and it's going to be flipped horizontally. So again, instead of a graph looking something like this to start off with, we're now looking at a graph that should look something like this. Let's go ahead and verify that with the graphing calculator. We'll clear out this data and try the graph. We have logarithm base 2 of -x, and there we go. When we compare that to the original, it's just a horizontal flip directly over the y-axis. Don't forget, too, that if this was perhaps multiplied by -2x on the inside, every x value on this graph has to be doubled. So instead of being at -1, 0, we'd be at -2, 0. And instead of at -0.5, -1, we'd be at -1, -1, and so on. All of these data points just gets shifted by doubling to the left, and that's going to create a graph that would be twice as wide as the original. And same thing would have occurred over here. Instead of just flipping the graph over vertically, each of these points gets doubled as well. And so what that's going to do for us is it's going to make our graph look like it's much taller. So we'll have less of an arc still, and it might point down this way. You'll see some examples of this in some of your practice problems tonight. There is one last type of exercise that I wanted to show you in this video because you'll encounter them with your practice problems tomorrow in class, and that's the ability to use existing points to find a function in the form of a logarithm. So what we have here is a logarithm that's a traditional shape. It's increasing as we go to the right, so I know it has to be of this basic form. It's going through the point 1, 0, so I know there's no flips or stretches or skews or anything like that. What we'd like to do with this is identify the function that would produce this curve that goes through our standard point and the point 5, 1. So the way we would approach something like this is to remember that a coordinate is comprised of both an x and a y value. And if we think of our standard form of a logarithm that looks like this, we're looking for the number 1, because that's our y value, is equal to the logarithm base a of 5. And to answer this, you could probably figure it out on your own, or you might recognize that this is one of our properties. Let's talk about figuring it out on our own first. A to the first power must equal 5. What would A have to be in order to make that true? Well, a to the first power equals 5. What would a have to be? Oops, not x. A has to be the number 5 itself. So really what we're dealing with is the logarithmic function y equals logarithm base 5 of x. This would be the answer to the question. And again, if you remember our properties, we can go back to the notes from yesterday and looking at this property, number 2, that's the one that said when the base and the target match, logarithm base a of a must be equal to 1. That's exactly what we had here. The logarithm base a of 5 had to be equal to 1. Well, in order to make that happen, this a value and this 5 had to be the same. A had to be equal to 5. And you could have answered that question without showing any math whatsoever because you remembered your properties. Let's try another one. This is perhaps a little bit more difficult. We again have a standard logarithm, and I know it's a standard logarithm because it's going through the point 1, 0. This time around, our y value is -1. Our x value is 1/2. So logarithm base a of 1/2 must be equal to -1. And again, if we immediately think of the equivalent exponential function, this should be a to the negative first power equals 1/2. And by calling upon our memory of exponential rules, a number raised to the negative first power simply rewrites this number as a fraction. A has to be equal to 2 because 2 to the negative first power would equal 1/2. So if a is equal to 2, then the equation y equals logarithm base 2 of x represents the equation for this entire graph. So think about those examples. We had 3 big concepts today. Solving for an equation based on a given graph, that was 1. Considering how a logarithmic graph can change by stretching or flipping, that's concept number 2. And then concept number 3 is again thinking about the family of functions. This is an overall discussion on how logarithmic graphs should always appear. Please be sure to ask questions tomorrow in class. Make note of the portions of this video that doesn't make sense or that you would like further clarification on, and I will be happy to help you in class tomorrow.